Okay, welcome to the Karma's DSP seminar. Today we have a very special guest, Dr. Jin-Woo Lee, or just Jin Lee. And in the announcement, it was written that he is a PhD candidate. But in the meanwhile, now he officially became a doctor. So he's now Dr. Jin Lee. He was a PhD student of Professor Kyoku Lee, who is one of Karma PhD alum, and Kyoku was a student of Julius Smith. So Dr. Jin Lee is also one of the grand students of Julius in that sense. Yeah. And today, Jin will share with us his research on differentiable physical modeling. And this research was accepted to New Risk to 2025 a few days ago, which means again, this research is very remarkable and meaningful in machine learning in general. So please welcome Dr. Jin Lee with a big clap.
Thank you. Thank you so much for having me on this beautiful day, and thank you so much for inviting me over to this beautiful place. It's actually my first time to visit Karma, and honestly, I was really surprised in 2 points. So I was first really fascinated by the exterior and the history of Karma, which was told by Suyeon. He really guided me pretty well. Really, I really appreciate his guidance.
Karma tour today.
Yeah, that was really awesome Karma tour. And also the second point was that I was really fascinated by how cutting edge and really advanced in the interior of this Karma. So I was really glad to be here. And yeah, let's get started. So yeah, a little bit more about me. So my name is Jin Lee. My legal name is actually Jin-Woo Lee, including the space, but please call me Jin. And yeah, I was recently graduated from Seoul National University, and I'm now doing an internship at Meta Reality Labs. You can find more about me in this webpage. So today I'm gonna present details about my research that was presented, that will be presented in the NeurIPS conference this year. And also I want to share a little bit more my ideas about underlying in doing this research, and some issues that I confronted, and my thoughts about how to tackle those issues. So hopefully we're gonna have discussions after this talk. And well, let me introduce from the beginning of my research interests. So my research interest is it's about how to synthesize a realistic sound using computers. And obviously there are many ways to do these realistic sounds, especially in defining realistic sounds. And my approach in pursuing this realism is to, well, it closely follows the spirit of physical modeling. So I'm more concerned about modeling these physical systems in the real world in the computers, so that we can mimic the physical systems that arise in the real world using the computers. And more specifically, my research interest is to, well, to embed those physical modeling systems in a differentiable way. So I'm actively studying physical modeling, numerical simulation, and machine learning. And regarding that, we can ask several questions, especially from the digital signal processing perspective. We can wonder, why should a physical modeling be differentiable? Because it's already, we can synthesize really good sounds and realistic sounds without using a differentiable physical modeling. My thought about the reason why, about the advantage of making physical modeling differentiable is that we can reduce the efforts in doing parameter tunings, and also my idea is about that we can somehow close the gap between this synthetic and the real measured sounds, so that we can bridge the gap between the physical modeling output and the real recorded measurement by using this end-to-end optimization process. And also, from the machine learning perspective, we can wonder what are the advantages of doing physical modeling, the perspective of neural network researchers. So for that, I think the biggest thing about doing physical modeling is about controllability. So especially for professional studio recording, if you think of a professional studio recording environment, what people want is a delicate and faithful or intuitive control of their instruments. So unwanted stochasticity is less preferred in this studio. Under this controlled setting of studio recordings. So in the concern about hallucinations, my idea is that designing these neural network architectures based on physical modeling theory can greatly reduce these concerns about hallucinations. And a little bit different perspective about hallucinations, which I really like about it, is that it can be also, I'm not saying that hallucination is something that should be removed. This hallucination, hallucination can be viewed as a really creative feature that can be created using AI technologies. So recalling back to the early days of computer music, so once these sound effects like glitches or clippings, and many of these sound effects are now really important components of our music technology. But once there was some time that they were considered something that should be removed, but now they are considered really important components. So like these examples, also hallucination can be interpreted as a creative component of our music, but that's another perspective. And I also like this perspective, but there is a big difference between being able to get rid of hallucination effects and having to live with them. So my thought is to first to learn how to try how to reduce these hallucinations, and a natural approach in doing that is to impose a proper inductive bias in the neural network architectures using physical modeling. So as a brief review about physical modeling and neural network musical sound synthesis, there is a systematic difference between those two. So beginning from the neural network, especially if you are talking about supervised learning setting, given that we have an input that can represent about the music that we want to synthesize, and we have a music data denoted there as Y, then once we know the target audio and the corresponding input representation, then we can train this neural network, here denoted as B of theta, to reduce its output, the gap between its output and the target data Y. So once we measure that loss, we can back-propagate to update the parameter of the neural network to minimize the loss using gradient descent usually. And the input representations are usually a tokenized codebook, or there can be neural network-based constructed codecs when we see most neural network-based music generation processes. On the other hand, for physics-based simulations, what we have to know is the input parameters. Those are usually initial conditions and material properties. Those are parameters for the corresponding physics simulator, which essentially simulates or computes the solution of our PDE of interest. So basically, if we're talking about sound synthesis, then this PDE will be a wave equation with proper boundary conditions that we are imposing. And this physics simulator are validated to closely mimic the real measurement. So based on that validation studies, we can simulate this physics simulator to have our output y tilde as a synthesized output. And since it's validated, this y tilde closely mimics the real recorded real measurement y here. And my approach in doing this neural network-based approach, differentiable, I thought of three approaches. So there are three approaches that I can call them as differentiable. And the first one is to keep that simulator's algorithm as is and simply implement that simulator using the differentiable languages or the packages that support computer-based gradient optimizations, gradient back-propagation optimizations. And more specifically, so this process is actually, it closely follows that of a physics simulation that we know. So given a physical parameter, this differentiable physics simulator outputs the simulated output y, and then once we can measure this loss between the simulated output and the real measurement y, and then once we can compute this y tilde over this difference of a physics parameter, so that this is differentiable, this physics simulator is differentiable, then we can update this input parameter p to reduce the loss between y tilde and y. And the second approach is to use the simulator as a dataset generator to train this neural network, which is more straightforward in the perspective of neural network researches. So we use this physics simulator as a dataset constructor for the input p and the target y tilde. So we are considering y tilde as a ground truth. And we can train this neural network to map from this parameter p to its output that can minimize the loss between the synthesized y tilde and its output y hat. And in doing that, in order to make the neural network's optimization better, we can auxiliarily use this approximated solution, which is essentially a solution for a simplified system for this physics simulator, so that neural network can use that solution to better optimize itself. And the third approach is on a little bit different context. So it's physics-informed optimization, also referred to as a physics-informed neural network. And the approach is to train this neural network to mimic to estimate the solution of this PDE that we want to train. So the neural network's input is the partial differential equations parameter and its variables space and time, and it's trained to estimate the corresponding partial differential equations solution. And in training that neural network, a characteristic thing about this physics-informed optimization is that we can use this computer's automatic gradient estimation functionality to measure the partial differential term in our PDE. So the loss is actually it's not measured as something of a difference between the output and the target, but rather they are defined as the differential term that is computed using this automatic gradient functionality. So the good thing about this approach is that we can train this neural network to estimate the partial differential equations solution free from any kind of a discretization configurations, which is pretty tricky, especially when we're doing a finite difference approximations or finite difference time domain. So the third approach is pretty efficient, and it can provide advantages in terms of discretizations, but it's a little bit of a red herring in this in the topic that I'm gonna present today. So you can find a little bit of my experiments about this third approach in my PhD thesis, but I'm gonna just skip about it on today's talk and more concentrate on the first two approaches. So, well, to say first, the differentiable model synthesis for physical modeling, the DMSP model that I'm going to present later, it falls into category of B, the second approach, and I'm still actively concerned about issues related to the first approach. So let's to briefly mention about the issues that I'm concerned about on the first approach is that when we keep this simulator as is, simulator's algorithm as is, and then try to optimize these parameters in gradient descent, we're essentially trying to solve this inverse problem for this observation y to estimate the underlying physics PDE parameters p. So it's actually ill-posed. So we're not assured for every time we can do convex optimizations. So there can be many local minima, and our we are prone to falling into the suboptimality when we are doing gradient descent by backpropagating through this physics simulator. And in the perspective of a systematic design, since this physics simulator is essentially an approximation about the system that we want to simulate, we can concern about its covering space, so how large it can cover, including the data that we want to synthesize. So it might be this covering space, it depends on our system design, but since we are designing the simulator first, and then try to optimize to fit its output to this target data, target measurement y, then we're not assured, we're not 100% sure to that have this target measurement y lies into this covering space of this physics simulator. So we can concern about the systematic design of its simulation itself. And the last thing about this keeping the simulator as is about efficiency. So especially when you try to backpropagate through a finite difference time domain simulator, then that actually computes recursively computes its partial differential equation solution in the resolution of time domain samples in each spatial paralleling is spatial domain. Then, actually the forward itself can take a few times, but the backpropagation through that time domain sampled recursion is pretty expensive, and also when we are thinking about implicit update about this finite difference scheme, then it takes way more time to do the recursive updates for the gradient backpropagations. So we're not sure to fully utilize the GPU parallelism that can greatly accelerate our optimization process. And regarding that issues, I tried some toy example experiments. So here, this toy example is to estimate the initial pressure field that can, so we initialize the pressure field and then we simulate our wave equation, and our target is the pressure field that we know at time step here defined as tau. So with this observation, we try to backpropagate from this time tau to the time equals 0, and then try to update this initial pressure field that can simulate that can recover this pressure field at our defined time equals tau. And for this case, our target pressure field looks pretty omnidirectional. So one candidate for our initial pressure field will be that of a monopole placed at the center of this gray square. Since this is too trivial, I prepared another pressure field, which apparently doesn't seem like a pressure field that was computed using wave equation. And then try to fit our initial pressure field to match this to recover this pressure field at time equals tau. So here is the video of my wave. So this is actually the answer about, I mean, it's not an answer, but the result about my initial pressure field. So when you see this video, it comes pretty fast, so you should pay attention a little bit. So, oh, sorry, that was a spoiler. When we play this video, there it is. So, yeah, this video is spanned from this time equals 0 to 2 times tau. So at the center of this video, we could see this picture of my face moves really fast. So when we see that picture, this experiment actually took about a few hours, or maybe 10 or 20 hours using CPU, of course. The hardware was not optimized well. It was not ideal, but the thing I want to mention about this experiment is that it kind of mimics, but it's not really close to the target of our problem definition. So there can be systematic mismatch between the covering space of our physics simulator and the target that we want to estimate. And also oh yes, question?
I'm just wondering, what are the parameters you are trying to optimize here?
Oh, the thing I want to optimize here is the initial pressure field. And so once we optimize this initial pressure field, and then the video I showed was just the solution obtained through this wave equation.
Also, it's the pressure field, as you can see. Yeah, is the pressure field a 2D matrix?
Oh, yeah, it's defined as a 2D matrix. Okay. Thanks. Oh, so the 2D matrix for this initial pressure field, and then it is iteratively updated in the evolution of time, for sure. Okay. Thank you for your question. And yeah, please feel free to interrupt anytime when you have a question. And also, I tried to implement that string sound synthesizer, which I closely followed the work from Professor Bilbao's studies. And I tried to implement Professor Bilbao's finite difference time domain simulator using a PyTorch package accelerated by C++ extensions. And my actual goal for doing this research was to implement that in a differentiable PyTorch-based finite difference time domain simulator. So I wanted to also implement the backward propagation for this string sound synthesizer, but it actually ended up as just forward iterative string sound synthesizer accelerated by CPUs and GPU computations based on users' convenience. And the reason why I didn't implement the backward propagation was that the first thing is this string sound synthesizer was already pretty slow to train a neural network based or gradient backpropagation based optimization. So even though this was implemented for a forward iterations, I could imagine how slow it would be for the backward backpropagations when we do that. And also, that's also related to the scheme I used. So I was using an implicit scheme, which requires a several inner loop to estimate a next time steps solutions based on the previous time step solutions. So, and also I was concerned about the three issues that I mentioned before. So, this work was ended up as a GPU accelerated finite difference scheme with the PyTorch implementations. And then I moved on to the second approach. So I started that research as to implement this first approach to keep the simulator as is and make it differentiable. But I rather tried the second approach because to me it was more obvious that this will work since we're using a physics simulator as a dataset generator, and we can simply train our neural network to mimic that simulator's response to these given physics parameters. So that work was coined as this DMSP that I'm going to present now. So it's essentially about nonlinear plucked string instrument simulator using neural networks. So the architecture is based on spectral modeling synthesis, and but it's parameterized by neural networks. So it's framed within neural network architecture, but it's the network design is based on spectral modeling synthesis with a model decomposition to incorporate the material properties and the physical parameters. And also, I tried residual learning that can, so I tried this DMSP model to utilize model solutions while estimating the nonlinear strings response to the given physics parameters. To expand more about that, so given mechanical properties like the initial condition for the plucked string, so actually the pluck of the string was defined as the initial condition rather than the pluck excitations. And for that initial condition and tension and stiffness parameters and lossiness parameters, we first derive the model solution based on that. So we can have a linear string response. And for computing that, we can try two approaches. One is to, well, try to estimate the mode using Newton equations, or we can try neural network to mimic that Newton method. And from that, so we have mode frequencies and mode amplitudes, and to estimate the nonlinear strings nonlinear partial differential equation solution, we further modulated the mode frequencies and mode amplitudes using neural networks to model the pitch glides or random partials that can be observed from the nonlinear strings sounds. And we could additionally leverage the noise injection, so we basically follow the additive synthesis approach in to better estimate the nonlinear sound synthesis. So after we estimate the output, we measure the loss between the ground truth, which is actually obtained using the finite difference time domain simulator that I mentioned before. So we can measure the loss between the ground truth and our output. And also, we additionally experimented using a pitch annotation and using the graph model. So we estimated the fundamental frequency from the finite difference time domain solutions, and then try to match the output of a frequency modulator to fit the difference between the fundamental frequency of a ground truth and its lowest value of a output mode frequencies.
Why do you need the AM and FM in that stage there? Can you clarify a little more why that? Yes, I was asking why, can you justify why you're using the AM and FM mid-stage there? What are the advantages in employing those?
Yeah, thank you for your question. So basically, this linear strings output, we also have really close mode frequencies and mode amplitudes, but the target of our interest is about nonlinear strings, which can have some kind of a pitch glides that where the pitch is they're kind of detuned, or they changes depending on the displacement of the string or how we plot the string. And also there can be phantom partials that is inharmonic peaks in the high frequency regions. This is also a characteristic trait of our nonlinear string sounds. So, and these pitch glides or phantom partials is not modeled in our model synthesis part. So, yeah, exactly. So our intention in there was to model this. Yeah.
So you're not just having harmonics, but you also have some kind of inharmonic components which are generated by the FM there.
Yeah. Exactly.
Thank you.
Thank you. Yeah, just to add a little bit more,
Yeah.
this linear string solution is also inharmonic, so it can, yeah, it depends on the stiffness of a string. But obviously, this nonlinear string sound is more inharmonic.
What are the relationship between the mechanical properties and control parameters? Are they separate or like one control the other?
This is just my. These were categorized by myself, so I'm not sure about any conventions here, but my intention in doing this was to, this is the mechanical properties that can be used for, those are explicitly, they can be explicitly used for the simulation of a partial differential equations to get the solutions of them. time and pickup position is actually the space in our PDE. So it's more like a variable for this time and pickup position. For the pitch is actually, yeah, it is a PDE parameter, but my intention in doing this division is that in the perspective of the users, think these variables are more frequently controlled by users, and these were well interpreted more like characteristic of a string's materials. So yeah.
So they are both optimized during the training?
No, actually, not exactly. So these are not optimized ones. So these are used as an input.
Okay.
Yeah, and then neural network is trained to estimate the corresponding PDE's output for those. So it's not keeping the simulator as is and do kind of a differential backpropagation, but yeah, we prepare the paired data for the ground truth simulations output and its corresponding PDE parameters, and then try to train this neural network to mimic the simulator's response rate.
So where's the neural network in this graph?
Oh, so yeah, so the neural network, so these, for this modulation part, these are neural networks, and the noise decoder here is also a neural network, and we can also optionally use a neural network for estimating the modes of these mechanical properties.
Okay, understood.
Thank you. So yeah, for this part, when we use our neural network for estimating the linear solution, we call it a DMSP hybrid model. No, sorry, that's a DMSP model, and if we use a Newton method, since it's a hybrid with a numerical iteration and a neural network, so we call it a DMSP hybrid model. And just to compare a little bit more, so we tried to compare this with several methodologies. The first thing is obviously model synthesis and finite difference time domain. And what we consider here is the simplest version of a model synthesis. So actually, I'm aware that there can be many extensions for a model synthesis for estimating nonlinear sounds, but what we mentioned about this model synthesis here is just a superposition of well, the mode frequencies and mode amplitudes. So model synthesis and FDTD, the finite difference time domain, they're physical modeling, so they can obviously model the physical properties. But the simplest version of a model solution is it can incorporate the linear solutions, and on the other hand, the FDTD can. They have many advantages for modeling the nonlinear and dynamic sounds, but both of them are not differentiable at this point. For model synthesis, we should pre-compute the mode first, and then use it for the inference, which can be done pretty fast. On the other hand, the FDTD requires comparably more computations because we have to recursively estimate the solutions for the number of samples, time samples, and the number of spaces. And another renowned approach in the neural network community in musical sound synthesis, DDSP model, differentiable digital signal processing, or nowadays more known as a differentiable spectral modeling approach. So the DDSP model cannot incorporate the physical properties, but they can efficiently synthesize the nonlinear sounds in a differentiable way. and it requires the recurgence of a number of frames because it operates on a short-time Fourier transformed spectrograms. And the proposed DMSP and the DMSP hybrid model is it can model the physical parameters, and they operate in a differentiable manner to estimate the nonlinear solutions. And there is no recurgence required for this estimation, and the only thing is that when we use the Newton method to measure the model frequencies, we are more assured to have the accurate model frequencies and both amplitudes, but it requires a pre-computation for obtaining that.
So looking at the last column there,
Okay.
you have the first one, which seems to be the least complex, the modal approach. Yes, the first row.
Yep.
Yeah, and then you have the FDTD, which is an X and T, and then an R there is the number of frames, overall frames. So how do the FDDT compare to the DDSP in terms of complexity?
Oh, so the question is about the difference between
Those two, yes, yes.
Yeah. So for the FDTD, usually the finite difference time domain requires the recurgence of this spatial dimension, and the time. This NT is a number of time samples in a waveform, more likely a waveform. So it requires more. It depends on the stability of this scheme, but it usually requires a small sized resolution. So it requires higher resolution for the time samples. On the other hand, the DSP model here, it requires the recurgence over the time frames, which is usually 100 times more, 100 times less iterations compared to this NT.
So it's more efficient at the end of the day.
It's
Thank
more
you.
efficient. Yep. And for the objective evaluation, so this is the evaluated result. So it's basically the difference measured in different metrics between each of these outputs and the result of a finite difference time domain. So here we are considering the FDTD result as a ground truth and try to estimate the difference between the trained ones and the non-trainable model synthesis output. So when we first see the nonlinear strings result, so this is the difference between the FDTD simulated using this alpha value larger than 1. So which this alpha value is actually the stiffness to tension ratio. So when we define this as a value larger than 1, then we can simulate the nonlinear string. And for estimating nonlinear strings response, the DMSP and the DMSP hybrid model outperform the other baselines. Here, the model synthesis is what I mentioned before, so it's approach to synthesize sound using superposition of mode frequencies and mode amplitudes. And DDSP-ish and DDSP-ish XFM here. Those two are the baselines that I also implemented. Those are close to DDSP model, where this DDSP-ish is it's based on a spectral modeling synthesis. It's similar to spectral modeling synthesis, but it doesn't incorporate the model solution. The model parameters as its input. And this DDSP-ish XFM model is that the similar one to the DDSP-ish, but it doesn't do the frequency modulation part. So comparing this DMSP and the DDSP-ish is the difference between those two are whether to impose the mechanical parameters as its prior or not. And when we see the linear result, so the target is the linear string sound. So here the model solution should be the solution itself, but there is a small difference, like a frequency-dependent damping factors. So it's not really 100% close to the FDTD result, but the pitch is the most accurate one, and this is because the model synthesis is actually the pitch is independent from the frequency-dependent damping terms, so it should be the most accurate one. But the DMSP hybrid model also closely follows the result of a model solution and the FDTD result. Also for the signal to distortion ratio or scale invariant SDR, the signal to distortion ratio, our model also performs pretty well for the linear solution. And I think the reason for being inferior compared to the non-linear parts, so our DMSP model's result is worse compared to our performance on the non-linear result. And what I think about that reason, so the reason why would be the sampling of our alpha value for the training set. So there were plenty of these alpha values larger than 1. So we sampled from 1 to 25, but there were not many samples with alpha value exactly to 1, which is the case of a test set here. So I think if we put more training data set for this linear string, I think the result will be also better for the linear string case. But since our scope was to estimate the nonlinear string better, so this result shows the effect of our DMSP approach. And also, this evaluation study is about the experiment between whether to use the additional fundamental frequency annotations. So actually, additionally using this fundamental frequency annotation and try to match its mode frequency output with that greatly improved the result, especially in the nonlinear string cases for both DMSP hybrid and the DMSP model. And you can see the result better when we see the video of that. So here I prepared 6 videos of our string. So the horizontal axis is about space, and the vertical axis represents the displacements of each string. And we can hear its sound picked up at its positions. And when we play it, we can first hear the ground truth of a finite difference time domain simulation. So there was a bit of a pitch glide and vibrato at the end of this video. And the model solution cannot incorporate that pitch glide, but can model the vibrato. So if you hear it, so it's a bit, so the spatial relation, as we can see, can be modeled pretty accurately, but the pitch glide is not modeled for the model solution. If you hear it again for the ground truth, there was pitch glide at the front of the time, but the solution is more like a constant fundamental frequency, and then puts a vibrato at the end. And if you don't use any kind of physical parameters as its input, so if you see these DDSP-ish models, we can those were prone to modeling the spatial relations, as we can see from this, even for the initial values. So the DSP-ish model, which incorporates frequency modulation part, it could well model some kind of a stiffness related in harmonics, but it was prone to modeling the spatial relations. But if we don't even use the frequency modulation part, then the DGSP-ish model cannot just model the inharmonicity, so it's more like a harmonic pitch skeleton. So when you hear it, we can hear the more harmonic sound. But when we fully utilize the both amplitudes and both frequencies, especially using the Newton method, then we can pretty accurately recover the finite difference time domain solution. So if you hear it for the DMSP hybrid, so if you hear it again for the ground truth, closely follows the ground truth. So for that case, the both frequencies and amplitudes were obtained using Newton method. And if we try to use the neural network to mimic that Newton iterations, we can be more efficient while retaining the result. So it's less accurate compared to the DMSP hybrid, but it's more efficient in estimating for the inference scenario. So, is there any questions so far?
So just to clarify, the hybrid has both the AM and FM modulation, the hybrid there?
Yeah, it incorporates AM and FM.
It's kind of a very interesting approach because classically you never find AM and FM applied for synthesis per se. I mean, yes, they used it for synthesis, but not in a broader spectrum environment. So, yeah.
So actually the modulation part, so
that part there.
yeah. And so actually this frequency modulation and the amplitude modulation is meant to say that the both frequencies and both amplitudes are further compensated by neural networks.
Yeah, right. Which is new, for me at least, a new thing. So.
Oh.
Yeah.
But it was kind of tricky to optimize using gradient descent to say, especially using, to training this neural network to estimate these mode frequencies. So that's why I use this additional loss term to enforce this output to match the fundamental frequencies.
Jinwoo? This is Malcolm. So your only criteria was pitch in this case?
Sorry, can you reiterate, please?
Was the only criteria in this case pitch?
Yes, exactly.
So there's nothing about timbre or anything else?
Yeah, timbres and the rest of the parts were optimized on this the actual output of it, and in terms of multi-resolution spectral loss. So the rest of the parts were measured at the end, and for the frequency value itself, I just measured for the fundamental frequency here.
Okay, thanks.
Yeah.
All right, thank you. So after we can approach the model pretty well using this neural network, can we go one forward step to use the model as a proxy and then go back to tune the parameters?
So is the question?
Say the ground truth is actually playing a recording of a violin note,
Mm-hmm.
and you use the model as a proxy of the simulated,
Yeah, that's a good point. I think so to do that, but there, I think there should be some more modules to do that framework, because first we need to have a measurement for each space and time. So for example, if you're talking about the string sound synthesis, then this output it's depicted as simply a spectrogram, but it's more like spectrogram for each spaces. So we also have a space dimension, and if we have a similar measurement, so if we measure the string's displacement in space and time, to say, for example, like using laser Doppler vibrometers. So using those equipments, if we have it, then I think we can do something similar approach. But yeah, I think it's worth trying, of course.
Test one. Well, that covered my question pretty well, but what does G stand for? Is that generation target?
GD here?
Yeah.
Oh, it's, sorry for the abbreviation, so it's more like a ground truth.
Ground truth.
Yeah.
And is it phase sensitive? So you mentioned a multi-resolution spectrogram comparison. Is it phase sensitive?
I think it's, yeah, I think actually it should be phase sensitive. In optimizing this, especially since we have to estimate the spatial relations, I think the phase should be estimated pretty accurately here. And I think, yeah, using only the magnitude of a spectrogram as a multi-resolution spectrogram loss, then we can, well, those phase informations can be disregarded for the optimization, so it can be hard to optimize. But yeah, so.
You also mentioned there's a space dimension and is there a frequency dimension? It's like time, it's space and frequency, are those the axes of the spectrogram?
Yes, exactly. So it's actually, for measuring this as a multi-resolution spectrogram loss, then there is a space, time, and frequency, where the time is actually the number of frames here.
Okay. So this is really going for an exact replica, independent of how we hear it. This is like, let's model this string, and that's why the waveforms, that's why the string shape looks comparable even at the very end of its vibration, because it's really trying to track the physics of that vibrating string. Yeah, that's a good acid test.
Thank you for thinking.
And I just have one more question since I have the mic. Why would you say modal is not differentiable?
So what I meant to, yeah, I agree that modal synthesis can naturally be differentiable. But what I meant before here was that what I meant here was to just to say the modal synthesis with the simplest version. So just a forward with the superposition of modes. But I agree that this modal synthesis can naturally be differentiable. But, yeah. Thank you for mentioning. So that DMSP approach was, as I mentioned before, it falls into this category of B. So it was using the simulator as a dataset generator, and then train our neural network to mimic that simulation. And going back to the issues that I was concerned about on this first approach, I could find some literatures, and I'm not, I'm sure that there are way more studies, those are concerned about the similar topics in various domains. And what I could find so far was to tackle the suboptimality issue, we can probably try some explorations like reinforcement learning. So, well, to say we can add some more explorations for the parameters that we want to optimize. or we can impose some better industrializations for that parameters. So especially when our simulator is highly recurrent. So it's also really renowned technique in neural network literatures, especially for modeling RNNs. And also we can simplify the gradient update rules. So especially in the reinforcement learning physics simulation domain, they usually use this softening technique for the unruly gradients. So there can be, so the reinforcement learning field also has many differentiable physics simulators, and they have many reports say there are unruly gradients, especially in the contact simulation or friction simulation. So for those simulations, we can do some kind of a softening, or we can do also gradient clipping to make our optimization landscape better. And since we are concerned about musical sound synthesis, there are also studies that mention about this similar suboptimality in frequency estimation. These are reported in many literatures that I listed below. So if we are to estimate the pure sinusoid frequency, so here this black dotted sinusoid is the target we want to estimate, and what we are doing here is to update this blue pure sinusoid's frequency using gradient descent. So when we backpropagate by measuring the spectral loss between these sinusoids, then the loss landscape looks like this. So the upper two rows here show the loss landscape of a spectral distance measured in L1 loss, and the logs, the similar L1 loss measured in the log spectrums. So what we see here is a actually constant value by 2, and then at the ground truth frequency, the loss suddenly becomes near to 0. And this means that when we try to optimize this sinusoid frequency using gradient descent, then the landscape is pretty flat here, so we're not really likely to smoothly converge to the ground truth. And it was proved that this unruly gradient region can be resolved by, for the case of a damped sinusoid. So undamped sinusoids have really unruly gradient, but if we have a damping factor, then the landscape, similar landscape becomes really smooth, and we're more likely to converge to the real ground truth frequency even by using this gradient descent. And more recent research reports that using a optimal transport as our loss update measurement is more advantageous, especially in terms of frequency estimation for pure sinusoids. So their approach in here is to use this optimal, is to construct a transport map in between the spectrums. So let's say the blue spectrum is our output, and the orange spectrum is the target we want to match. Then when we estimate the loss in terms of MSS loss, the multi-resolution spectrum loss, then the loss landscape looks like this, and the measurement, the minimization criterion is measured as a green line here. But if we construct a optimization map, then we can impose the update rule by minimizing the green lines like this. So it's minimizing the transportation cost in between the spectrum energies between the sinusoids. So when we do that similar experiment for the pure sinusoids, the first row is the loss measured using a simple MSS loss, and the second row is the loss landscape using the spectral optimal transport loss. And you can see that the loss landscape is really smooth, and we're really likely to converge to the ground truth. And if we even impose the damping, the gradient, the difference of a loss with respect to the frequency it becomes even smoother, and we have exactly 0 at the ground truth frequency, so we can converge pretty well. And but some reports also there are some reports that the optimal transport can be so imposing the optimal transport is it can be not a some kind of silver bullet. So of course it works, and it's really advantageous in making this update smooth. But this is another work done in the computer vision community, and their approach is to optimize the viewpoint and the lightning source that can recover the rendering of our geometry here. So there are geometry and the defined RGB values for the corresponding meshes, and our task is to optimize this viewpoint or the lightning source by observing these projections on these 2D images. And their approach is to optimize our parameters using the information of our optimal transportation maps cost that is measured using the RGB values and the position of the mesh. But so the optimality, so for using that optimal transport map and make the gradient update smoother, it really depends on how the optimality is defined. And in defining that optimality, sometimes they require the underlying assumptions in our task. And the underlying assumption in this work is that there are not many candidates that can be mapped with a similar color, similar RGB values, and those candidates are located nearby this the original observation. But if we think of this case, for example, like the target is to rotate the initial pattern, which looks like this wooden panel, and the task is to rotate it with 90 degree. Yeah. So of course the others also fail to rotate this initial viewpoint with a 90 degree to match this target projection. But since they report that there were too many candidates for each RGB pixels to be mapped, and their optimal transport map was not constructed ideally. So there was also a report that this optimality can be dependent on how we define the optimal transport. And also about the generalizability. So my concern about this generalizability capability of our physics simulator and updating our parameters using gradient descent, I think I could get some hint from the work from Professor Julius's done in 1995. So basically my thought about the hint from this work is that, well, so this systematic design of a simulator essentially it's an approximation, and my concern was that how detailed should it be to fully cover our simulator's output covering space that can fully cover the real measurement target data. And my concern was like how detailed should it be? But actually, what I got a hint from Professor Julius is that it doesn't need to be really detailed, especially when we think of a committed piano synthesis like this. There should be, so if you think of synthesizing guitar sounds or piano sounds, there should be many components, even disregarding the strings. So there should be bodies or soundboards or even a recording room. So those many components should be also modeled, but on the other hand, if we define our string model as a linear system, those can be also commuted as the second row here, since all of those, the other parts are also modeled as a linear system. We can commute these linear systems and then embed our the complex parts as a target of our optimization. So, of course, I still need to check if the validity of this idea in doing it as a gradient descent, but I think that this could be probably another breakthrough. And my conclusion or my thought at this point is that this physics simulator doesn't need to be really detailed to fully cover the output space, because that can be modeled by optimizing these parameters, and if you allow that optimization can embed those concerns, then this physics simulator doesn't essentially need to be detailed. And also about the efficiency, I was concerned about the validity of back-propagating through many number of iterations. But there are also really active researches. Those are aimed to accelerate the nonlinear recursions with fully leveraging the parallelism of a GPU or similar hardwares. So one approach could be simplify the nonlinear recurrence. Those can be observed in many line of works like sashimi or S4 Mamba. So we can actually make the recurrence linear and then impose the pointwise nonlinearity at the end of it, and just and this kind of replacement can be done because we are actually training the linear recurrence, and this system is trained in an end-to-end manner. And also, if we keep the nonlinear recurrence, there are also works that reports that this nonlinear recurrence can be learned in a parallel manner. So it's more like it's a bit different approach, because usually the nonlinear recurrence should be occurred in the order of its recurrence, but the idea is to update these nonlinearly recurred values with auxiliarily iterating, like Newton method or Levenberg-Markov method. So there are also active research in the neural network community about reducing the cost of a nonlinear recurrence. So if we take advantage of these researches, this efficiency regarding the many number of recurrences in our physics simulator could be also resolved in my thought. So, well, to mention about key takeaways, I thought of implementing differentiable physical modeling, and for that I tried 3 approaches, which I mentioned the 2 of them here. And the first approach is to keep the simulator's algorithm as is and then implement that algorithm using the differentiable packages or differentiable programming languages. And there were some issues that I was concerned, and I'm actually still actively thinking about how to resolve these issues. And while doing that, I also tried the second approach, which is to use the simulator as a dataset constructor and then train a neural network to mimic that. And for that, my architectural choice was to use a spectral modeling synthesis. And I also tried other architectures like more usual choice in the neural network community, like UNets or WaveNets. But also I tried some more neural network community preferred training methods, like framed in the diffusion frames or using a transformer networks. But well, at this point, I found that spectral modeling synthesis architecture was more likely to simulate the spatial relations. And also using the residual learning with leveraging the model solution was really helpful, and also the additional pitch annotation was really helpful in stabilizing the gradient optimization. And also there is a demo page for this work. So I prepared this demo using a Hugging Face, and you can control the temporal length and spatial resolution, and you can control many physical parameters, and you'll see the spectrograms and the videos with the sound. So please try that, and thank you for listening. Yeah.
Everyone feels good, or everyone feels hungry? Yeah, actually, we're gonna have more time with Jean outside having dinner together. So if you get more questions while having dinner, feel free to ask him, and we'll still have him around Karma. So, okay, so thank you for coming to Karma DSP seminar, and thank you very much for Dr. Jin Lee for this amazing presentation of his PhD research. So yeah, it was a great day, and we're gonna have dinner there. Okay, great, thank you.
For inviting me.